this is the William Seeley Gosset Lecture, which is presented by ISBIS, this award in recognition of outstanding statistical work that furthers the mission of our society. It was awarded first time in Bill Meeker in 2015, so it's awarded at every ISI World Statistical Congress, then Vijay Nair in 2017, David Banks in 2019, and then now Galit Shmueli in 2021. Galit is Distinguished Professor at the National Tsing Hua University in Taiwan, where she's also the Director of the Service Innovation Center. After getting her PhD from Technion, Israel Institute of Technology, she spent some time at the Carnegie Mellon and University of Maryland, USA. Shmueli teaches and researches on data mining, forecasting analytics, interactive visualization, research methods, and other business analytics topics. She's inaugural editor-in-chief of the new Informs Journal on Data Science. Her research areas include the time series, data mining, and sampling. She's author or co-author of many books and was recently elected as a fellow of the IMS. It's a great pleasure, it's a great honor for us to have Galit giving this lecture. Galit, the floor is yours. You have 45 minutes, and then people can ask questions through the chat. Thank you.
Thank you very much, Fabrizio. 1 second. Let me share here. So this is indeed a very big honor for me to give the fourth Gosset lecture. And the topic that I gave, the language of statistics and what's lost in translation, might sound a little bit mysterious. Those who've read the abstract have maybe some idea of what I'm going to be talking about. But this is the first time I'm giving this talk. So there's going to be a lot of thoughts, running through my head and your head at the same time. Before I go any further, I do want to say again, thank you very much for giving me this opportunity to deliver the Gosset lecture this year. And it's a real honor, especially given the outstanding researchers who've received it before me. And I'm delighted to see Bill Meeker at this ungodly hour joining us here. And Vijay Nair and David Banks, all amazing people, that I've met and known. And really, it's a big honor to be part of this series. So as I was going to prepare my Gosset lecture, I wanted to first know more about Gosset. Now, I did know that he worked for the Guinness Brewery. And indeed, if you go to Wikipedia, they tell you Gosset was an English statistician, chemist, and brewer who worked as head brewer and head experimental brewer of Guinness and was a pioneer of modern statistics. So in today's language, we would probably say that Gosset was the chief data scientist at the Guinness Brewery. But going a little bit more into depth, I also knew that Gosset was the famous student from the student t-test, but I still wanted to learn more. And there's a really wonderful chapter about him in a book by David Salzberg. The book is called A Lady Tasting Tea, and the chapter is called That Dear Mr. Gosset. And from there, I learned that Gosset's first paper actually arose from the need to figure out how much yeast to add to mash for making beer. And he determined that the counts of yeast cells could be modeled with a Poisson distribution. Now, this was quite an outstanding application and revelation of the usefulness of the statistical distributions at the time. So Gosset wanted to publish it. But the problem was that it was against company policy to allow publications by its employees that would disclose either the name of the company or the name of the authors. So eventually, Carl Pearson, who was one of the editors of Biometrica, helped Gosset publish the paper under the pseudonym Student. So his first paper was actually about the Poisson distribution. And over the next 30 years, Student wrote a series of extremely important papers, almost all of them printed in Biometrica. And at some point, the funny part is that the Guinness family discovered that their dear Mr. Gosset had been secretly writing and publishing scientific papers, contrary to the company policy, but I guess it was a bit too late at that point. So let me go back to Gosset's original task. He was trying to determine the amount of yeast to add to mash. And in the book, Salzberg tells the following story. The measurement was the count of yeast cells in the sample, but the real thing that was sought was the concentration of yeast cells in the entire jar. Since the yeast was alive and the cells were constantly multiplying and dividing, this thing did not really exist. What did exist in some sense was the probability distribution of yeast cells per unit volume. In other words, the revelation was dealing with things that do not exist. And this brings me to the topic of my talk today, which is the language of statistics. One of the founders of the 20th century linguistics, Ferdinand Saussure, said, "Without language, thought is a vague, uncharted nebula." The famous mathematician Bertrand Russell said, "Language serves not only to express thought, but to make possible thoughts which could not exist without it." And this relates to what I would like to talk about today, which is how does this language that we use, the language of statistics, how does it limit our thoughts? And more than that, how can we actually discover these blind spots or these unknown unknowns? So I'm not a linguist and I have no proficiency in linguistics. So I'm going to be using loosely a few terms that I borrowed from Cambridge Dictionary. I'm going to use the word terminology, meaning special words or expressions used in relation to a particular subject or activity. I'm going to use the word language for statistical language, as in the special words and phrases used by statisticians, right? People who do a particular type of work. I'm going to use vocabulary, meaning all the words that exist in a particular language or subject. And lastly, I'll use the term notation or statistical notation, a system of written symbols used especially in mathematics or to represent musical notes. Okay, let me start by saying what I'm not going to talk about. I'm not going to talk about two things. I'm not going to talk about awkward terms in statistics, things like regression, where, first time encounters of the word regression think that you're regressing in your mind, or terms like linear regression that make people think that they can only be used to fit linear relationships, or things like logistic regression, where my MBAs always thinks it's logistics regression. Or even words that are difficult to spell or to pronounce, especially if you're not an English speaker, such as multicollinearity or heteroskedasticity or, supercalifragilisticexpialidocious. We're not going to talk about those. I'm also not going to talk about misinterpreted statistical terms. And in the last few years, we've had a plethora of, outcries about misunderstandings of p-values and statistical significance. I mean, these issues have been around for a long time. There's old papers. This is a paper by Mark Shervish in 1996 about p-values, what they are and what they are not. Of course, more recently, we have papers such as the one in Nature Methods on interpreting p-values. And there are also some papers with exotic names, such as A Dirty Dozen, 12 p-value misconceptions. So this is not what I'm going to talk about today. But what I do plan to talk about is about missing notation and missing terms that I encountered that I feel show that our field really has a lot of momentum to sort of push forward and get some more of these. So I'm going to take you through my journey and talk about three specific encounters where I was missing either terminology or notation in order to describe the world and be able to use my statistical toolkit. The first one will relate to my work on explaining versus predicting and the statistical science paper that was published in 2010. The second is work with Ron Kennett on information quality, which was published in the Royal Statistical Society, and also we have a Wiley book. And the third is a recent and ongoing work on quote unquote improving prediction. So let me start with the first journey. In the first journey, to explain or to predict, I had both problems. I had missing terminology and I had the problem with missing notation. For those of you who are not familiar with the paper or who didn't attend the talk that I gave, the keynote when was it, a year or two ago at the ISBIS in Malaysia, in a nutshell, this paper did three things. First of all, it clearly defined terminology. What does it mean to explain? What is explanatory modeling? What does it mean to predict? And what does it mean to describe? Apparently, there are completely different meanings in different fields. And even within statistics, there was a lot of confusion. This is 2010. The second part was discussing how in different fields in academia and industry, there are monopolies. In some fields, they only do explanatory modeling. In other fields, they only do predictive modeling. And then the core of the paper was talking about why these different kinds of modelings are different and how they're different, how evaluating statistical explanatory power is different from evaluating predictive power, and so on and so forth. So when I started out, I had to define terminology. I had to explain that explanatory modeling and predictive modeling mean different things to statisticians, to social scientists, to computer scientists, to other scientists, to lay people, to journalists. They mean completely different things. So one thing that I did early up front was to give my definitions, my definition of explanatory modeling was really the way I was seeing it being used by my colleagues in management and in social sciences, which is explanatory-based statistical testing of causal hypotheses. And for them, explanatory power was really the strength of the relationship in a statistical model. In contrast, I defined predictive modeling as an empirical method for predicting new observations. And by the way, empirical method is a term that's not familiar to many statisticians. As one of the reviewers of my paper said, I don't even know what that means. Empirical can mean any method that uses data. So it could be a statistical model, it could be a machine learning algorithm, it could be a simulation, it could be anything. And I also defined predictive power as the ability to accurately predict new observations. So I needed to very clearly define what these were, and it wasn't very obvious what to do. The next part was trying to explain why these different kinds of modeling are different. And I tried in different ways. So at first, when I wrote up the paper, I tried to explain it in words. I tried to explain that these different modeling approaches have different scientific goals. They try to generalize differently. Their generalizations are different. Although in statistics, we usually just talk about sample to population, some of these talk about different kinds of generalization. And the third thing is that they have a different estimand or predicand, and those are actually terms that we do use in statistics. So for example, in explanatory modeling, the goal is to test or estimate a causal effect between constructs. Constructs are not measurable variables. These are some kinds of abstractions of concepts that we care about. Things like well-being, things like happiness. Those are constructs. Those are things that are heavily used in social science. And also the unit of interest there is the average population unit. In contrast, in a predictive model, we're trying to predict values, actual numerical values or text values for near future individual units. And descriptive modeling is a third thing that's different. There we're interested in testing or estimating a distribution or a correlation structure, again for an average population unit, but we're looking here at the measurement level. We're not looking at any constructs. So this was one attempt to try and explain why these different modelings were different. I try to use just words in English. Then I try to use pictures. So if any of you has attended any of my talks on Explain or Predict, I show this beautiful Van Gogh painting, and I tell the story of how Van Gogh might have been sitting right across from this village when he was in asylum and painting this beautiful village, imagining him sitting right there. And suppose that you're a historian who's trying to now figure out how life was going on in this village, and all you have, the village is gone, all you have is Van Gogh's painting. And if that's the case, then you really hope that Van Gogh was really, very sharp and not on too many medications and too crazy, so that the village that you see here really reflects as much as possible the truth of the village life back then. Was the church next to the houses? Did the river flow next to the forest? Or what was really going on? In contrast, if you were a museum restorer and you received this painting that had a terrible, ugly patch right there, then your goal would be very different. You really wouldn't care about whether the church was next to the houses and where the river was flowing. You would care more about the brushstrokes and the types of paints that were used, and maybe the exact information that's around that little ugly blocked spot there. And in that sense, the restorer cares more about the level of the data. It doesn't care about the truth that was used to generate this painting. And that's one big difference between explaining and predicting. I then try to take this kind of description and put it back into words using terms borrowed from the social sciences. So I explain in the paper, measurable data are not accurate representations of their underlying constructs. The operationalization of theories and constructs into statistical models and measurable data creates a disparity between the ability to explain phenomena at the conceptual level and the ability to generate predictions at the measurable level. So I was trying every possible way of communication to tell why I think these things are different. And when I submitted this paper to Statistical Science, one of the reviewers came back, and here's what they wrote. They wrote, I did have difficulties in reading the paper. I don't think I've ever read a statistics paper without formulas, except for the appendix. I had considerable difficulties along these lines because of insufficient vocabulary to be sure that I would know what you were talking about. And in the first draft of the paper, indeed, I tried words as much as I could. So when I revised the paper, I really took this reviewer's comment to heart. It was a very difficult comment to address because I didn't really know how to address it, but it took me some time. And in the end, what I did was the following. I said, in an attempt to make the paper leaner and crisper and to make the reading easier for the audience, I've included some mathematical notation to define the problem more formally. Let me show you what I did in the paper. So in the paper, I introduced two sets of notations. For measurable variables and statistical model, I used the ordinary things that we're used to, you know, X and Y for denoting random variables or expected values, for E's for expected values, and F for statistical functions. But then in orange, you see here, I use things that are at the theoretical abstract level. So for constructs, I use this calligraphic font. It's just a different font for X and Y. And for a causal relationship where X causes Y, I had to use this, you know, calligraphic F in orange here. And here's a little snippet from the paper where you can actually see these two kinds of fonts showing up in different places. And hopefully this made things a little bit easier for the readers. But what this also helped me understand when I did this, and this was a fantastic comment from the reviewer, was that this also helped me better explain and understand for myself how my work was different from the very famous paper by Leo Breiman in 2001 in statistical science, which is called Statistical Modeling the Two Cultures. Leo Breiman was focusing mostly on the difference between machine learners who are trying to predict the Y's and statisticians who are interested in estimating the F's. So you see that they're two different pieces of the measurable world, but you'll notice that Breiman doesn't go and talk about the constructs and the theoretical models because that was in a third different world that didn't really touch on his paper. So I would say I'm not even talking about two cultures in my paper, we're talking about even three cultures. So then putting it all together, I had to do two things. First is I had to clarify terminology, things that people were using casually, but had no definition. And then I had to add notation, in this case, in a very funny way. I basically used a new different kind of font. After I did this, it was much easier to explain better the remainder of the paper. So for example, I said, if you want to contrast explanatory modeling with predictive modeling, there are 5 aspects you want to consider. One is how heavy the theory is versus the data. And then when I'm talking about theory, I can talk about all these constructs and concepts. Whereas when I'm talking about data, I'm talking about measurable data. I'm talking about the range of causation to association, how much weight you have on retrospective versus prospective on this scale. We have, of course, the bias variance trade-off, and that's very easy for statisticians to understand because that's statistical notation. And finally, talking about whether we're looking at the average unit or the individual unit. So that's the first journey. The second journey is called InfoQ, or information quality. And in this journey that both Ron Kennett and I walked together for a long time, we again stumbled on missing terminology and missing notation. So let me start by a very nice book by David Hand that's called Statistics, A Very Short Introduction, where he says statisticians working in a research environment may well have to explain that the data are inadequate to answer a particular question. And the work that Ron Kennett and I were trying to answer, the question we were trying to answer was, can we find a way to say, what is the potential of a data set X, a specific data set, to achieve a specific analysis goal? And it seems like a straightforward question, but in fact, nobody asked this question in a direct way, and it's not written up anywhere. So we wrote a paper first that eventually got published in the JRSSA with many interesting comments that follow. And you'll notice that this paper was published in 2014, but when we submitted it, it was 5 years earlier in 2009. And this just tells you how difficult it is to have a communication within our community when there is no notation or vocabulary that everybody's used to. So we had to introduce new words and everybody had to understand what we're talking about and we had to be clear about it. And that's why the book was also very helpful, where we could expand on not only notation and words, but we could also give a lot of case studies so that people would be able to relate to their own world more easily. So in a nutshell, what is this InfoQ? Again, our goal is to measure the potential of a certain data set to answer a goal of interest. And the first thing that we had to do is we sat together and we thought, what are the major components in this problem? And we came up with these four based on both of our experiences. We have a goal, an analysis goal. We have the data. We have an analysis, some kind of a method or methods. And then we have the utility of this whole analysis. After we did this, we asked ourselves, which of these is actually a statistical term? So data and analysis, yeah, those are statistical terms. If we use those with statisticians, everybody knows what we're talking about. But if I use the word goal, or if I use the word utility, that's a little more tricky. Utility, some areas in statistics will have a utility function, or in economics, but utility more generally is actually pretty ambiguous. Which of these has statistical notation? Again, for data, we have plenty of notation. For analysis, we do. But for goal and for utility in a general way, that's not so clear. So the first step is we had to define these components and we gave them names. So we used notation. So, X for data and F for data analysis methods, that's standard. But then we used G for goal and U for utility. And it seems very simple and naive. And it looks like, oh, now you have 4 random variables or 4 functions, but it's actually more complex than that. The next step is after we created these notations, and I'll get back to them and explain what they are, is we put them together in order to define what InfoQ is. How does InfoQ put these 4 things together? And we defined InfoQ as the utility U of applying a data analysis method F to data set X conditional on the goal of your analysis. Now, this looks like just a simple probability formula. Everything looks straightforward, but in fact, it's hiding more than it's actually showing here. And to show you why things are hiding, I'll just mention that the third step was to try and relate the quality of each one of the components to the quality of the overall information, what we called information quality. People would ask us, isn't this just data quality? And we'd have to explain why it is not data quality. So let me go briefly through these 4 components and show you how their quality is different from the whole info quality. And you'll see where the notation and terminology issues come in. So let me start with goal. Goal is a tricky thing because anyone who's done an applied statistics project or worked with industry or with a non-statistician collaborator, there's a domain goal and there's an analytics or a statistical goal. The domain goal is what the scientist or the business person or the industry person wants to answer a question, a what, why, when, where, or how kind of question. And then we as statisticians need to figure out how to translate it into an analysis goal. What does that mean? Well, I need to know, does this person want an explanatory goal? Is this a predictive goal? Is this a descriptive goal? Or in words of Deming, is this enumerative or analytic? Or Tukey's words, exploratory, confirmatory? There are lots of different types of things, but there's no real definition of what is a statistical goal. And once we've chosen the type of goal, we have to say, okay, what kind of hypothesis are we building? So G here is not really a random variable. And it's not really a function, it's actually a construct. It's an abstraction. It's something that we do from our experience in our heads by communicating with a domain expert. And when we think about what is the quality of goal specification, one thing that comes to mind is Kimball's error of the third kind, giving the right answer to the wrong question. Or Tukey had many famous sayings, right? For example, he said, far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise. Notice Tukey's distinction between the vague domain goals and the very precise analytic goals. So this is a tricky type of term that just putting a G notation on it doesn't really solve it. It's still an issue. Then we move to more familiar land. So X for data, yeah, everybody understands, in statistics, what it means when we talk about the source of the data or the data types or the data size and dimension. This is easy. But what this helped us now was to explain why data quality is different from InfoQ. So for example, data quality, there are 3 different definitions of data quality. And all of them show you that they measure some kind of a utility of the data given a goal. But you'll notice that what's missing here is F. There's no analysis in here. For example, Mallow's 0th problem, which is how the data relate to the problem and what other data might be relevant, This is about data, about the goal, right, the problem, and the utility of using the data, but they don't mention a specific data analysis method. They don't say, how's this going to be useful if you're using a linear regression or if you're using a designed experiment? There's nothing to do with what kind of analysis you're going to be using. In management information systems or in databases, they define data quality as the usefulness of queried data to the person querying it. So here is just a querying operation. There's no data analysis that happens beyond that. And even organizations such as the IMF, OECD, or general administrative statistics organizations, they have something called the quality of statistical data, which is typically the usefulness of summary statistics for some particular goal, for a decision maker. So they're the only kind of analysis, there's no analysis, it's just a summary statistics. And what we were saying was that InfoQ is more general than this. This is a special case of InfoQ, where the F here is summary statistics, but we want to talk about something more general. The third component is also well-known territory. It's F for the data analysis method. And here we said, the type of method could be statistical models, machine learning algorithms, econometric models, optimization or simulation if you're an operations research person, or even graphical methods and models. Those can all fall under the F. And the quality of the analysis here would, of course, affect the InfoQ, but it's not the same. So, for example, Godfrey said that low quality analysis is poor models and poor analysis techniques, or even analyzing the data in a totally incorrect way. This heavily depends on analyst expertise and experience. Sometimes it depends on the software availability that you have. And in fact, data analysis quality is the focus of statistics and data science education in general. The last component is, again, tricky. It's like the goal, and the utility is, again, where we tie back and need to talk to the domain expert who's going to consume or use the analysis that we generate. So the analysis utility is something that we do as statisticians within our own analysis, and we have plenty of performance measures, anything from predictive accuracy to statistical significance, goodness of fit, right, expected costs, and things like that. We have plenty of those. But those are not typically the domain utility. The person who's consuming the result doesn't really care about the statistical significance, doesn't care about an R-square. They care more about maybe something like a key performance indicator or KPI, or how they will be able to implement this method within their organization. So once again, U is not just a function, and it's not a random variable. It is a construct that has multiple levels here. So when we talk about the quality of utility measure, we're talking about both metrics from the statistical standpoint, but also metrics from the domain standpoint. So thus far, I showed you what we did when we embarked on this InfoQ journey. First, we had to define the relevant components that build the InfoQ, give them names or notation. In the second step, we put them together to create InfoQ with a notation of its own and a formula. And in the third step, that allowed us to study how quality of the different components related to InfoQ. The fourth step, and the last step I'll tell you about, is the question of how do you actually put this in reality? This is not a theoretical question. We wanted to create a tool that people can use. You get a data set and you ask, what's the information quality in this data set? So how do you assess InfoQ? Do you give it a number? How does it work? And this again, we again had a problem, because realizing that InfoQ itself is a construct, we had to figure out how to operationalize it, how to measure it. And there we had to resort again to more of our social science experts and colleagues. And the idea of what they do there is they will take a construct like this and break it down into dimensions. So for example, we took InfoQ and we broke it down to 8 dimensions, such as data resolution, data structure, data integration, things like that. And then for each one of these dimensions, we created questions for the analyst to answer. And each one of them, you could have a scale from 1 to 5 or 1 to 7 or whatever that is. So that when you have a data set and you have a goal in mind and utility, this leads you through a checklist that at the end of the day will tell you how good this data set is, maybe compared to another data set, so that you can decide whether you want to purchase it, use it, deploy it, not use it, and so on and so forth. So going forward with InfoQ, and I think InfoQ is for sure not done, there's a lot more interesting things to be done, is the statistics, the language of statistics, have sufficient terminology and notation to express all these situations that we need to answer as analysts. Do they have notation for things that are really important and part of the things that we do, but maybe we just don't give them names and not very crisp definitions? The third and last part is an ongoing work that I started working on, I think about a year and a half ago, and it's called improving, in quotes, prediction. And here I'm going to show you something pretty interesting about missing notation and how I solved it in some kind of a hacking way, which led me to some very interesting discoveries. So the full name of this work is Improving Prediction of Human Behavior Using Behavior Modification. And it's based on what's going on right now with the big platforms who collect a lot of data about us and use it for predicting our behavior. Many of you have probably read the books of Yuval Noah Harari, the famous historian, or maybe you've heard him speak on different, he's been speaking in so many different places. There's an interesting TED interview where he says the following: the ability to hack human beings means the ability to understand humans better than they understand themselves, which means being able to predict their choices, to manipulate their emotions, and to make decisions for them. And my work is based on this interesting combination of predicting and manipulating people. So if you're thinking of the big platforms, these are just 4, but there are plenty other ones. Digital platforms collect lots of behavioral data about us, and they use it to predict our future behaviors. I mean, if you're using any social media, if we're even now using the conference website that's allowing us to chat and interact with different people, if you're using Uber, if you're watching Netflix or Apple TV or Hulu or streaming or using online dating or, you know, any of these platforms, of course, a lot of your data is being collected and it is being used to predict your future behavior. Why do these platforms want to predict your behavior? Because they want to improve their products and services or do what they call personalization. They use it for fraud detection, for advertising, that's a big model, for marketing, for logistics, for operations. So a lot of predictions go on right there. What kind of behaviors do they predict? Here are very popular ones that are being predicted. They want to predict what the probability is that you will purchase something or that you will leave. They want to predict how long you will be on the site or on the app. They want to predict your emotional state, predicting voting intentions, voting behaviors, and even predicting life events, right? Remember the famous Target story with predicting people who were pregnant, women who were pregnant, or predicting people who are going to be leaving their job or retiring or anything like that. So prediction is a big business. And of course, prediction efforts, you know, we're experts in it, right? In statistics and machine learning, that's a big thing. What is the approach that we take as statisticians? Is, you know, we'll have the X's, which are the inputs, and we have a Y, that's the behavior that we're trying to predict, such as the one in the green here. And then we take a big data set and we build a model, f of X, which is our predictive model. And then we can use this predictive model to predict the outcome for new people. So I will then get a Y hat, which is the brown circle right here. But of course, my predictions are not perfect. So there will be some discrepancy between the green and the brown circles, the actual and the predicted behavior. And that's our prediction error. How can we improve our predictions? Well, we can build better predictive models and better predictive approaches and methodologies. We can get better data. We know that that definitely helps. And if we're doing very heavy computing, then better computing infrastructure can also help improve predictions. And that's exactly what these platforms are doing. They're hiring plenty of statisticians and data scientists who design better approaches and better methods and models. And then they also purchase many companies. For example, if you think about how Google purchased YouTube and Facebook purchased Instagram, when they purchase them, they get a lot better data for prediction. And of course, these companies also develop their own computing infrastructure, even Uber does. And then they even sometimes sell us their infrastructure. As researchers, we can use that infrastructure. Now, let me also mention the superpower. So platforms can not only predict our behaviors, but they also can modify our behaviors using something called behavior modification techniques. And the way they use these techniques is to change users' behaviors in a specific direction. What kind of behaviors do they change? The exact same kinds of behaviors that we talked about earlier that they want to predict. So they can change the chance that we buy something. They can make us less likely to leave. They can engage us and keep us longer on our phones. They can change and manipulate our emotional states. they can change our voting intentions and voting behaviors, and they can even change some of our life events. So when you have these two powers in the same place, that sounds pretty powerful. Now, behavior modification techniques arose out of psychology in the world of behaviorism in psychology. And initially it was designed to help people and therapists to help humans basically hack themselves to get rid of bad habits and to get good habits going. So the idea is to use your lower brain and kind of ingrain a lot of good habits and get rid of bad habits. Later on, the behavioral economists figured that out and they said, oh, this is great, let's hack the system so that we can use this for policy. So if you think about policies that change an opt-in to opt-out, like organ donation, for example, that's an example of using these kinds of behavior modification techniques. And more recently, the human-computer interaction professionals have decided to take ownership of these techniques. And when they put them into a digital technology, it's called persuasive technology. This was named by the famous BJ Fogg from Stanford. And these are the folks who also train many of the entrepreneurs that go on and open the new companies such as Instagram and other apps and websites. And when it's persuasive technology, the idea is to hack your lower brain so that the interface itself can modify your behavior. You might have heard of methods such as tuning and nudging, which means planting subliminal cues in the context, or herding and tunneling, where you're manipulating or engineering the context, or even conditioning, where you have reinforcement reward schedules. I'll give you an example. If you have a phone and it has notifications on, what happens when there's a notification? It either pings or the light comes on, and then you will look at it, and then you will touch it, click the right button, which will take you to the exact place that it's intended to take you. And that's what's called behavior modification techniques that lead your behavior in a certain direction.
Galit, you have 8 more minutes, okay?
Yes. Okay, so now the question is how to improve prediction if you can also modify behavior. We mentioned earlier that we can just do the traditional approach, right? Build better models, get better data and computing infrastructure. But then I thought to myself, hold on a minute. If I can manipulate people's behaviors, there's another way I can show you that I can predict really well. That is by generating a prediction, but then pushing users' behaviors towards their prediction. So how would this work? Here's what we had before. And now I'm going to bring in the behavior modification approach. Now we're going to manipulate the behavior of the platform, which will manipulate the user's mental state, which would push the user's behavior towards the prediction, resulting in a much smaller prediction error. And now it looks like my prediction errors are much smaller and I can predict much better. Now, how does this happen on platforms? I'm not necessarily claiming this is intentional, so I'm not sure, I don't think the CEOs of these companies are setting up to do this, but the platforms are now using algorithms called reinforcement learning that combine prediction and behavior modification in them. This is not supervised or unsupervised learning. This is a different paradigm of machine learning. And if you think about it, it's a combination of testing and predictive models. So something like an A/B test with a predictive model, but then you do it multiple times. So you do a test, you get the feedback from the user, and you predict and get feedback, predict and get feedback. A very popular way is what's called multi-arm bandits or contextual multi-arm bandits, where again, there's a feedback loop where you don't just collect data from the user, but you actually do something to the user and collect feedback in return. And many of these platforms are now using these kinds of methods. Here's a little slide that I stole from Netflix online, and they show that using these contextual multi-arm bandits improves a lot their ability to keep people longer on their platform. So the point is like this: the platform can improve their prediction in 2 steps. First, they generate predictions, and then they push the user's outcomes towards the predictions. The challenge that I had was I wanted to describe this scenario with statistical notation so that I can compute things like the expected prediction error. But in statistics, we have beautiful notation for prediction, but we have totally different and separate notation for causal relationships that live in a different world and uses different notation. But there isn't one that does both. So when I was trying to write an equation for both, I had a problem. The way I solved it was I started with a normal, ordinary predictive notation. So I have the y given x as a function of x, and then I have the y hat as the f hat. And then I wanted to introduce the second step of behavior modification. So now what I did was I introduced Judea-Pearl's do operator. And do of a certain random variable means that that variable there is something that you can intervene on. You can decide whether you're doing it or not, whether it's treatment A or treatment B. So now what I'm interested in is the behavior Y conditional on the platform's behavior do, because the platform can control its own behavior. And I started using this notation, and to make it shorter, I just used a Y tilde to denote that this is a manipulated outcome. And you'll notice that there's a tilde on top of the Y and a tilde on top of the epsilon, and I can use a completely different function here. Doing this, I was able to at least talk about the quantity that I'm interested in, which is this improved prediction error, Y tilde, right, which is the manipulated Y, minus the Y hat. And I'm not going to get into the details of how I did this, but I just want to show you the before and after. So this is the classic expected prediction error function. There's nothing new here. This is the bias variance function. And then the next thing is I derived the equivalent when there is manipulation in there. And with manipulation, you'll notice that there are two new terms in here. One here is CATE, the conditional average treatment effect, or basically the conditional average behavior modification magnitude for a user with profile X. And you can notice here that this CATE, if it's exactly equal to minus bias, it cancels out the bias. But in fact, it doesn't need to be exactly equal to minus bias. It could just be opposite sign, but kind of same magnitude. Another interesting piece here is the sigma square tilde, which is now talking about how you can modify even the variability. So not only will you make people more close to their predictions, but you'll make people with the same profile more similar to each other. Again, I'm not going to get into what I did there. You can look at the papers on arXiv. I'm still writing it up and I'm going to submit it to a journal. But the point is that internet platforms now combine prediction and behavior modification, and that this approach is absent from statistics and machine learning literature, probably because it's two different communities who do experiments and the ones who do prediction. I solved it by introducing this do operator from Perl into the world of prediction. And I think that this combination can also be used to describe other strategies that combine prediction and manipulation. But again, it shows that you need sometimes to borrow new things. So I showed you my 3 encounters, but by far I'm not the only one encountering this. And if you just look at some other people's papers, you'll see this. For example, these terms reproducibility, repeatability, and replicability. Do we have statistical notations for each and every one of these? Do we have exact definitions? It's really ambiguous. Ron and I wrote a little piece about this. In a paper from 2020 in the Proceedings of the National Academy of Sciences, Bin Yu and Count Kumbier wrote about veridical data science. They invented this new term, and they said that this is a framework of predictability, computability, and stability. So you see they're introducing new terms because these things were missing from the vocabulary. Brad Efron, in a recent JASA paper that was also published in the ISR, has introduced the term attribution, which he uses for the assignment of significance to individual predictors. And if we think about notation, I showed you Perl's do operator, which was very useful for me, but Perl indeed talked about the gap between the vocabulary in which we cast causal questions and the traditional vocabulary in which we communicate scientific theories. He introduced the whole notion of causal diagrams as a fundamental piece that's missing in order to talk about causality when we're doing statistical work. Similarly, Don Rubin has a lot of work on the counterfactual and potential outcome frameworks. And again, they coined this whole notion of potential outcomes. And if you look at the notations that they use, they also have funky notation, right? They use these subscripts to denote different potential outcomes. So with this, I'm going to close and say the language of statistics is very rich, it's precise, it's rigorous, and it's been used to answer lots of important questions. However, it is still a young field, and the limitations of this language really keep important problems out of sight. We do have these blind sites. And the problem is that this hampers communications with non-statisticians. which means that when we collaborate with non-statisticians, this helps us identify these blind spots. By working with someone who is a non-statistician and trying to understand their scenario or their problem, and then trying to translate it into statistics and realizing, wait, we don't actually have words for this, or we don't have notation, this is where we can expand our language, which will then, of course, expand our field. So can we describe new scenarios and needs with statistical terminology or notation? The other question we want to ask is, what can we actually learn and borrow from other fields? Do they have the notations? Do they have terminology? Is it enough for what we need? Or if not, how do we move forward? In other words, let's just keep our open students mindset. Thank you very much.
Thanks a lot, Galit. It was excellent talk.